Hey, welcome back. In this video, we're going to continue discussing graph parameters that are used in the design of VLSI circuits. As a reminder, VLSI stands for Very Large Scale Integration. And when we were designing VLSI circuits, we discussed one way to deal with crossing wires in these circuits. And the method that we discussed was using this thing called contact cuts, where if we have two wires that cross in our circuit, one of the wires has to change its layer. And we do this for each contact cut. So the more contact cuts we have, the more area that our circuit is going to take, and the more likely that it's going to be faulty. So when we were discussing the crossing number, we tried to minimize the number of contact cuts, which was the same as minimizing the number of crossings. And so that was a natural graph parameter to define, was the minimum number of crossings that we could have in a plane drawing of our graph. Now, for some graphs, like we saw with the complete graph, for the complete graph of order n, the crossing number was theta of n to the fourth. So it was on the order of n to the fourth. And for a complete bipartite graph with both parts of size n, that one also we saw the crossing number was on the order of n to the fourth. So in the last video, we proved both upper and lower bounds to get theta of n to the fourth for both of those families of graphs. So complete graphs of order n and complete bipartite graphs with both parts of size n. So those are some examples of families of graphs where if we try to use contact cuts, we're going to have a lot of contact cuts. Because no matter how we draw those graphs, there's always going to be a lot of crossings. There's always going to be at least on the order of the number of vertices to the fourth. So when we have a lot of crossings, like in those families of graphs, there's another method that we can use for designing the circuit instead of using contact cuts. So instead of trying to minimize the number of crossings, we can decompose our graph, like decompose the graph that we are representing the chip with. We decompose it into a bunch of planar subgraphs. So we're decomposing our circuit into a bunch of planar subcircuits. And for each of the planar subgraphs, we assign the wires in that planar subgraph to a distinct layer. So we're breaking up our circuit into multiple layers, and each layer gets a different planar subgraph. And naturally, we want to minimize the number of layers that we use. And in other words, we want to minimize the number of planar subgraphs that we use. And so this is how we define the thickness. So let's define that explicitly though. So given some graph G, we define the thickness, which we denote theta of G, and it is just the minimum number of planar graphs whose union is G. So we can define the thickness as that, and that's the exact thing that we were describing on the previous slide, or at least it's equivalent to what we were describing on the previous slide. And just like we saw with the crossing number, planar graphs have crossing number 0. Well, analogously, we can say that planar graphs have thickness of 1 because it only takes one layer to represent a planar graph in layers of planar graphs. And anything of thickness 1, by definition, is planar. We can also get a pretty quick lower bound on the thickness of any graph in terms of its number of edges and its order. So if we have some graph G with order at least 3, otherwise that denominator becomes 0 or negative, and that would be a problem. So the order is at least 3. We can say that the thickness of G is at least its number of edges divided by 3n minus 6, where n is the order. And we can think about, why is this true? And we see something here which looks very familiar. We've seen this quantity before. 3n minus 6 right there. That's the number of edges in a maximal planar graph of order n. So if you take any maximal planar graph of order n, it's going to have 3n minus 6 edges. And so any planar graph of order n has at most 3n minus 6 edges. So if we decompose G as a union of planar graphs, each of those planar graphs has at most 3n minus 6 edges in it. So if G has a total of e edges, we need to take those e edges and fit them into planar graphs. We can only put at most 3n minus 6 of the e edges into each of the planar graphs. So the number of planar graphs we need is going to be at least e over 3n minus 6. Because if we had fewer planar graphs than that, then we wouldn't be able to fit all the edges. So you can think about it pretty much like pigeonhole principle. Each planar graph you can think of as a hole. So the planar graphs they are the holes, and the edges of G are the pigeons. So we know that each hole can fit at most 3n minus 6 pigeons. So our graph G has order n. So each of these planar graphs have order at most n. And that means each of them has the most 3n minus 6 edges. So each of these holes can fit at most 3n minus 6 pigeons, because each pigeon's an edge. So all that we're saying here is that theta of G, the thickness, which is the number of planar graphs, which is the number of holes. So number of holes is just greater than or equal to the number of edges, which is the number of pigeons, divided by the most number of pigeons we can fit in each hole. And another way to say that is number of pigeons. So this is totally equivalent. Number of pigeons is less than or equal to the number of holes times max number of pigeons in any hole. So number of pigeons, E, is less than or equal to number of holes, theta of G, times maximum number of pigeons in any hole, which is 3n minus 6. So that hopefully clears up that bound. And so I leave as a problem to you a very similar bound. And I might need to clear a little bit for you to see this, unless I'm able to do some translation. So here we go. Let's see. Good. Okay. So there it is. So here's the problem for you to think about. So prove or disprove that if G is triangle free and has E edges and order n, then the thickness of G is at least E over 2n minus 4. So here the 2n minus 4, that might look kind of familiar. So remember, this was a bound, we proved this, on the maximum number of edges in a bipartite planar graph of order n. So in the planar graph video, we proved that this was an upper bound on the number of edges in a bipartite planar graph of order n. And then in class, we showed that it was a tight upper bound. So we constructed some bipartite planar graphs of order n with exactly this many edges. Now, this problem is not about bipartite planar graphs. It's about triangle-free graphs. So triangle-free. So we know that all bipartite graphs are triangle-free, but there are triangle-free graphs which are not bipartite. For example, here's one which is triangle-free but not bipartite. C5. Not bipartite, but triangle-free. The thing is, though, that when we prove this result, the maximum number of edges in a bipartite planar graph of order n, our proof did not use the fact that the graph was bipartite. The only fact that the proof used was that the graph was triangle-free. So I claim if you use the same proof that we used in that video, you can also get a bound on the maximum number of edges in a triangle-free planar graph of order n. And using that, that should help to get the bound, this lower bound on thickness that you're trying to prove. And that's all I'll mention for that. So I'd briefly like to talk about what's known in terms of the complexity of thickness and the last graph parameter that we were talking about in the earlier video for this week, which is the crossing number. So computing the crossing number of a given graph is NP hard. And we talked about what this means in an earlier video. So NP hard means that any problem in the complexity class NP can be reduced to computing CR of G using a polynomial time reduction. And we can say the same about computing the thickness. So computing the thickness theta of G, this is also an NP hard problem. So we can say that this problem is as difficult as any problem in NP. Both of these problems, computing the crossing number and computing the thickness in general, are both as hard as any of the problems in NP. Now, if we don't care about computing them exactly, if we just want to approximate them, the crossing number in general for bounded degree graphs, you can approximate it within a polylogarithmic factor, and that's polylogarithmic in the order of the graph G, so in the number of vertices in G. And this approximation can be done in polynomial time. Again, that's polynomial in the number of vertices of G. On the other hand, for thickness, we can get a better guarantee for approximating the thickness. So even though both the crossing number and the thickness are NP hard to compute in general, for approximation, we can approximate the thickness within a factor of 3. We can do this in polynomial time. Again, the polynomial time is in the order of the given graph. So I'd like to discuss how we can approximate the thickness within a factor of 3. And in order to do that, we need to discuss another graph parameter, and this parameter is known as arboricity. So arboricity, we will denote this as y of g. And the arboricity y of g of some graph g is just the minimum number of forests whose union is g. So notice this looks like the thickness. So the definition looks exactly almost like the thickness definition, except we're changing one thing. Except we have forests instead of planar graphs. So with arboricity, we don't just want these subgraphs to be planar, we want them to be forests. So forests are a kind of planar graph, but not all planar graphs are forests. So the arboricity restrictions are more restrictive than the restrictions for thickness. So we can observe that a graph G is a forest if and only if its arboricity is 1. So obviously a forest is going to have an arboricity of 1. And any graph with an arboricity of 1 is going to be a forest. So we get this if and only if. And here's a problem for you to think about, kind of similar to some of the inequalities that we saw on the earlier slide. So prove or disprove that if G has E edges and N vertices, then the arboricity of G is at least the number of edges in G divided by the number of vertices minus 1. And notice that this bound that we see here, it looks similar to the ones on the earlier slide, except the denominator is the different part. So on the earlier slide, the denominator was 3n minus 6 when we were just considering the thickness of any graph with E edges and N vertices. And then when we were considering triangle-free graphs, we got 2n minus 4 in the denominator instead of 3n minus 6. So here we're getting n minus 1. So n minus 1, what does this quantity have to do with y of g? Well, y of g is the arboricity. So y of g, we're decomposing our graph into forests. So we should think about forests. How many edges do you have in a forest? And so I'll leave that problem to you to think about. So one thing that we can observe immediately is that the thickness of G is at most the arboricity of G. So we can consider a decomposition of G into forests, and we can specify that this is a decomposition of G into Y of G forests. So y of g, the arboricity of g, is the minimum number of forests we need to write g as the union of them. So there's some way to decompose g into y of g forests. Each of those forests is planar because forests in general are planar. So that tells us that we can decompose g into y of g planar graphs. So that means that the thickness of g is at most y of g. So that's how we get the inequality in this bullet. So we have an upper bound on the thickness, and that's just the arboricity. And I'll also note, without explaining this algorithm, because that would take a whole different video, there is an algorithm. It runs in polynomial time and the number of vertices in G to compute the arboricity of G. So there's a polynomial time algorithm to compute the arboricity of G. And using that algorithm, we can compute the arboricity of any graph in polynomial time and the number of vertices. And this is how we're going to find an approximation algorithm for the thickness. So even though we noted that it's NP hard to compute thickness, so we noted on the earlier slide, NP hard to compute the thickness, but we're going to see that there's a polynomial time algorithm to approximate the thickness within a factor of 3. And in particular, all we have to do is to compute the arboricity. And in order to see that computing the arboricity suffices to compute the thickness within a factor of 3, we have to prove one more inequality. So we have an inequality that the thickness is less than or equal to the arboricity. We also need an inequality in the other direction. And our inequality in the other direction, to show that we can approximate the thickness within a factor of 3, we're going to prove that 3 times the thickness is greater than or equal to the arboricity. In other words, the arboricity is less than or equal to 3 times the thickness. And in order to prove that, it suffices to prove a fact about planar graphs decomposing into forests. So I claim that all you need to prove is the next statement, which I'm going to leave as a problem to you, but then we'll talk about why this statement gives us what we want it to. So here's the problem for you to prove. Prove that every planar graph can be drawn as the union of at most 3 forests. So any planar graph is the union of at most 3 forests, possibly fewer than 3, but you only need at most 3 forests to represent any planar graph. And assuming that this is true, so I'll leave this as a problem for you to think about, but assuming that that's true, then we can suppose that we have a drawing of G, and we decompose G into theta of G planar graphs. So by definition of thickness, there exists some way to decompose G into theta of G planar graphs. And so if we knew that every planar graph is the union of at most 3 forests, then this would imply that we can decompose G into less than or equal to 3 theta of G forests, because each planar graph and the decomposition up here, each of those planar graphs we can represent as the union of at most 3 forests. And there's theta of g of those planar graphs. So we end up with at most 3 times theta g forests. And that tells us that the arboricity of g is at most 3 times theta of g, because we can decompose g into at most 3 times theta of g forests. So by definition, that's an upper bound of 3 times theta of g on the arboricity. So we do get exactly this bound that we want, which gives us the 3 approximation that we want. And all that it relies on is proving this problem that I leave to you. Prove that every planar graph is the union of at most 3 forests. And so before we finish this video, I should give you a helpful hint for this problem. So what's a good hint? So a natural hint for this one, I mean, there should be multiple ways to do this, but the way that I like is a nice induction. You can do a weak induction, a strong induction, whatever you like. Might as well do it strong. You don't lose anything that way. But I don't think it needs to be strong. And in particular, you want to induct on the order. So I'll leave that to you. And that brings us to the end of this video. So we will see more about the complexity class NP and finding algorithms for certain graph parameters in the next videos. Thanks for watching.